quality of an injection molded part depends on 5 important elements. That is the, somehow there is a delay, yeah. That is the product design and the knowledge about the materials, how dedicatedly, no, how dedicatedly you have developed the mold, the type of the molding machine on which the product has produced, and finally the process parameters by which the product is produced. These 5 important elements are interrelated with each other. Somehow I'm feeling some delay when I click the button. So there is a bit, okay. So these 5 variables are interrelated with each other, and creating harmony and synchronization in these variables can result into development of a very good product with close dimensional tolerances. For example, we know that the design of a product, if you have a better design, it would result into ease of molding that will lead to the cost savings. If the part is difficult to mold, then the product designer should realize that his design may undergo changes or alteration process so that it can be molded readily. The final properties of the product depends on these 5 variables. So it means that there is no room for over the wall thinking. A product designer, a material expert or a material supplier, a mold designer, a process engineer must work concurrently to develop a product. uh, and probably it is much necessary that these people should meet regularly during different phases of the product development. By definition, injection molding is a simple process. For example, it consists of merely 4 steps, that is the plastification of the pellets, injecting the resin into the mold, solidifying the mold in the mold cavity, and then ejecting the part from the mold. But in reality, injection molding is one of the most complicated processes. The process depends on 19 variables, and at least there are 11 to 13 variables which dictate the quality of the product. The complexity becomes even the worst. Oh, I don't know why it is changing automatically now. Yeah, so the complexity becomes even worse when we alter one variable, and because of this alteration, it could affect other 2 variables. So this makes the process very, very complicated. So how we can optimize the injection molding process? There are a number of ways by which we can optimize the process. I would suggest 6 ways to optimize the process, starting from the best to the least possible way. For example, mold simulation studies. Nowadays, it is a common practice to carry out mold stimulation studies before a mold is cut. So mold simulation studies give us important information, especially to the product designer. He can rethink about his design, whether his design is suitable for the molding process, or what kind of defects are going to arise during the injection molding under a certain processing conditions. For example, where the welding lines will appear, how the surface would look like, how much shrinkage the material will going to develop during the processing, and so forth. So such kind of pre-injection molding studies are always like very important for developing the best quality in the injection molded parts. Second option is to design the experiments. Although I would admit that it is a bit tedious process and probably in the production environment, it is not feasible as well. But here the universities and probably the research centers can play their part. So they have the arrangement of people who have expertise in the simulation and professors with immense knowledge about the behavior of the material and the processing condition. So probably the best place for such kind of studies is our universities and research centers. Then one can look at the recommendations of our material suppliers. For example, if a material supplier recommends a melt temperature range between 250 to 300 degrees centigrade, so the best way is to start from the midpoint. Let's say take the temperature 275 degrees centigrade and then go up and down little bit to optimize the process. So this way you can develop an optimum process, but it will be through trial and error method. Previous experience with similar geometries and material grades, especially if your injection molding process is a well documented process. You can go back and see that when, where, and why some defects arise and how they can be fixed. The fifth option is to look at the databases such as Campus for the issues related to the materials. And finally, you can make an educational guess. But this educational guess should not be impulsive in nature, but it should be done with a proper coordination between your colleagues, experts, and all the stakeholders in the injection molding process. So how an ideal injection molding process looks like. An ideal injection molding process should be robust, repeatable, and reproducible. The overall aim is definitely to produce the polymer parts with the quality and with the best consistency so that you will have a less rejection rate. Consistency can be of three types. Cavity to cavity consistency, for example, if your mold has 8 cavities, then the parts produced in the each cavity should have the same quality. For example, the first part should have the same quality as the fourth part or the eighth part in your mold. Then you have short to short consistency. Any part which falls out from the injection molding machine should have a regular consistency. Then you should have run to run consistency. For example, you have made one run and then you shift it to another mold. You do the second shot and probably then you shift back to the first mold again. Then it should give you the same consistency and the same results. An optimized injection molding process is just like driving a cruise control car on an open road, so that you don't need to have to stop again and again, fix the errors, because once you will do this process again and again, stopping the process, fixing the errors, it will definitely going to produce quality issues in the parts. So what are the sources of errors? The errors actually comes from different locations. It could be because of the process. As I said that there are 11 to 13 variables which could affect the quality of an injection molded part. The error could be because of the personnel involved in the injection molding process, especially if you have a semi-automated injection molding process. It may happen that some errors would result because of the personal negligence. And then the can come from the environment. from the ambient environment. For example, if the day is very humid, so it would happen that the weld lines in your molded part could be very weak. So if you don't have the proper venting conditions, or the proper venting control in the injection molding machine, then the errors can come from the material, especially if you are using the internally generated recycling scrap from, for example, when you crush and grind the scrap, and you scratch and grind the scrap, and during the transportation, maybe it may happen that some impurities will enter into your material, and it can affect the quality of your parts. Or it could happen like you are using a certain batch, maybe there is a problem in the batch, so which can affect the quality of the part. And then can be some measurement issues. For example, it could happen that the barrel temperature of your injection molding machine is totally different from the melt temperature, or the pressure sensors, they are not working properly. Then the errors can come from the machine as well. Suppose that your backflow valve is not working properly because of it has undergone through the wear and tear process. So during the packing stage, it will not provide enough packing pressure. So these are the different sources of error, and they have to be minimized. So one defect could have multiple causes, and it could have multiple solutions as well. So not what now what I'm going to do is to pick a defect, and I would try to correlate it to the 5 important elements of the injection molding. So one of the recurring defect which normally arises in the injection molding are the sink marks. Sink marks are normally Sink marks are the defects which normally appear on rib structures and bosses. So a rib that is thick in relation to the flange thickness will result in a significant sinking on the flat side of the part. Sometimes sink marks are cosmetic in nature, and sometimes they give so hideous look to your part that you have no choice but to reject the part. So how a sink mark is developed? When a liquid polymer enters into the mold cavity, and as soon as it touches the cavity surface, it immediately solidifies. So a solid skin is produced, whereas the underneath soft material develops the bubble. And as the bubble collapses, it pulls the solidified surface towards itself. And so a sink mark is developed in the material. So now we will see that how we can fix this problem by going through the 5 elements I described earlier. So I should little bit, I want to go back again. Yeah, sink mark is actually related to the localized cooling effect. So if there is a problem in localized cooling, that's a part of the uh, uh, a mold part is like the part you are developing in the cavity is one part is solidifying differently as compared to the other part, it will develop the sink mark. So we know that it is related to the shrinkage problem. So the best way to look at the problems related to the shrinkage is to look at the molding diagram. So when we look at the molding diagram, we observe that we have a relationship between the injection temperature and the holding pressure. So the way by which the molding diagram is depicted diagram is constructed is by creating two extreme conditions. For example, we see that in case of injection temperature, if the temperature is too low, we develop the short shots. And if the temperature is too high, we develop the thermal degradation of the polymer. Similarly, if the pressure is too high, it results in developing the, and whereas if the pressure is too low, then it results in developing of the shrinkage. So a good part always lies between the two extreme positions. So now we have pointed out that the shrinkage is caused by the holding pressure. So the best way is to look at the pressure diagram. So when it comes to the pressure, there are like four important settings which we have to manage in order to produce or get rid of the sink marks. And that is the hold pressure and hold pressure time, injection speed, fill time, and velocity pressure switchover point. In many machines, there is a direct relationship between the pressure and the injection speed, which means that if you want to achieve maximum screw speed, you must also have the maximum injection pressure. So when we look at the pressure diagram, we observe that the pressure diagram has specific features. For example, during the injection stage in which the ramps move forward in the barrel, it takes only less than a 1 second. And then we have a time decreasing depending pressure profile. So now the question is, why do we need such kind of a profile? The answer is that as soon as the liquid polymer is injected into the mold, it attains the molecules attains directionality in the direction parallel to the applied pressure. So now we have molecules oriented parallel to the applied pressure, whereas the underneath soft polymer has still the molecules in the coiled form, which is their natural tendency to develop the shape. So during the solidifying and shrinkage stage, these polymer molecules apply a pressure on the oriented molecules. And as a result of it, during the solidification stage, the part can develop distortion. And especially if you have fibers in your resin, then you are more likely to develop the surface related issues. Hold pressure. So pressure should be viewed in context with the polymer type. In amorphous polymers, normally you want to have as low pressure as possible, but it should be high enough to avoid the sink marks. In semi-crystalline materials, you should try to use the highest possible pressure to get higher crystallinity, lower shrinkage, and higher strength. Now the question arises how high we can go in hold pressure. The thing is, until you get the flash in the parting line of the mold, or until you get ejection problems. What hold pressure time should we use? Regarding the amorphous polymers, as short as possible until you do not develop sink marks. So whereas in case of semi-crystalline materials, you should think differently. Why semi-crystalline materials require a different behavior? Because when the polymer melts develop the crystals, it results into compacting the polymer molecules. And as a result of it, you produce large shrinkage in the material. So, and when you increase the pressure too much, you produce even better compact structure in the crystals. So the higher pressure actually helps to develop better crystalline structure in the polymers. And the other fact is that these amorphous polymers, they undergo only 5% shrinkage, whereas the crystalline polymers or semi-crystalline polymers, they have the ability to undergo up till like 10% shrinkage during the solidification process. So it means that you need to inject more and more liquid polymer in case of the semi-crystalline polymers. And then when we think about the hold pressure, it is also important to take into account the part thickness as well. Since the polymers are not good conductors of heat, so it means that if you will increase the wall thickness, it will have less solidification effect. So, for example, in case of polyamide 6,6, you need 2 to 3 seconds per millimeter, whereas in case of acetal, which has a higher crystallinity as compared to polyamide 6 required 7 to 8 seconds per millimeter. The hold pressure time, and this diagram shows a relationship between the mold shrinkage and the hold pressure time. So again, we are using the acetal material. The hold pressure is 90 megapascal, mold temperature is 90 degrees centigrade, and the melt temperature is 215 degrees centigrade. So under these processing conditions, we observe that while we change the thickness of the mold, we have to change the hold pressure time as well. And the parts with the higher wall thickness requires longer hold pressure time. Another important study which can be performed regarding the shrinkage in the polymers is by doing the study between hold pressure and percentage shrinkage. And in production environment, this kind of study is bit difficult. But what you can do is to study the weight change in response to the hold pressure time. So we observe that, for example, when we have a small hold pressure time, the shrinkage is we do not attain the full weight of the polymer. And as we increase the hold pressure time, we reach a saturation point around 30 seconds, where we achieve the maximum weight which could be developed in the part. And this is the time where if we go slightly above this time, it is okay. But if we are below this time, we will definitely develop sink marks in the sample. So the black line shows us the relationship between the hold pressure time and the percentage shrinkage which develops in the material. So more or less the same time we develop the minimum shrinkage when we develop the maximum weight in the part. Another way of fixing this sinking defect is to increase the hold pressure switch point. So the hold pressure or a VP switch point is the point where you change the switch the ramps first in the injection molding process. The ramp moves forward, so it is dictated by the speed of the ramp. And when you have attained at least like 95, you have filled the mold cavity 90%, then you switch it over to the hold pressure. Normally you will have a cushion of 5 to 10 millimeters. If you slightly increase the this switch over point, you will better produce the parts which will and you can get rid of the sink marks. Then I will try to now correlate with the mold design, the same defect. So the same defect can be avoided by having a good mold design. So the mold design, for example, the solidification of the part depends on the cooling channel design, their size and distribution in the mold. And then it also depends on the gate type, gate size, and gate location. For example, if you have a tunnel gate, it freezes off much quickly than the edge gate. So the premature freeze off will reduce the available packing time in the cavity. Okay, so I will try to wind up my discussion. So it may happen that your material will solidify much earlier than the gates will solidify much earlier than the part which is being molded. So it is advisable over here to use the proper gate. For example, you can locate if you have located the gate on the thin part, it's going to produce the cavity in the part. But if you have transferred it to the thicker part, then there are less chances to develop the cavity. So it may happen that there is a fault in your molding machine. So if the backflow valve has suffered wear and tear, it may happen that during the packing stage you are applying the pressure, but the polymer is going to leak through the backflow valve and it will develop the sink mark. When it comes to the product design, so you have to be very careful around the corners. The corners should be uniform. They should not be thick and should have the acute angle. When providing the red eye, so sometimes the product designers are too generous in providing the radiuses, and that results in developing the thick parts. So these are the places where the sink marks could develop. Finally, I would say that if your sink marks are of cosmetic nature, then there are ways by which you can disguise the sink mark. For example, by creating grooves or by creating beads opposite to the rib, or by creating a surface texture in your part. And sometimes as a final uh, the molders use the blowing agents which can get rid of the sink marks. So last thing is, we know that the materials which shrink more have more ability to develop the sink marks. So this is what I would like to say. And there could be some other reasons as well which could either develop sink marks, or you can get rid of the sink marks. So thank you, Essen. Now you have the control.
Yes, thank you very much. Stefan, if there was any questions in the chat.
Thank you. No, actually not. So you are free to continue, but feel free to send in questions in the chat also during Tor's presentation.
Yes, please do not hesitate to send us questions. Tor, please, the scene is yours.
Thank you. Good morning, everyone. Again, my name is Thor Gardarsson, as was already explained. And my background is in polymer science, and my role in Thule has been for the last 3 years to support our product development with materials selection and processing of injection molded parts, amongst some other things, but that's the point for this presentation. I also would just point out in this picture here, so you understand a little bit of the background as to the examples I will show later on. The type of products that Thule makes are often used outdoors. We make a lot of equipment that allows our customers to bring their hobbies and their activities outside with them. So the connection, I would say, to injection molding that you understand is that we often make plastic parts that both have a structural component to it or have mechanical requirements, but also aesthetic requirements. So you can see here that the car has a roof rack and a roof cargo box, but it also has a bicycle carrier on the back. So obviously there are both mechanical requirements related to these products, but they should also look appealing, and balancing those requirements is something that is obviously connected to the quality of the part. So I have some examples that talk a bit about this. And I'd like to thank Professor Kadir for his presentation. Some of this will be a repetition, but I will add my twist to it. So when I speak internally also to my colleagues about what determines part quality, I focus on these 6 items, and I've highlighted the first 3 in bold because I would argue that if those are not taken care of, then there's limitations to what you can actually do to improve quality with the selection of the injection molding machine, the process parameters, and other auxiliary systems. So I would say I might be experiencing a delay as well. Let's see if it pops up. There we go. Part design, that includes everything from wall thickness to the gate location to how you've designed the rib structure. Some of that already Professor Katir discussed. Material selection, you obviously need to understand the requirements for your part to choose the right material, but then also the design of the mold. The mold is the positive or the negative, depending on the way you see it, but the partner for the part. And then of course, once you have a part designed and ready to go, then the selection of the machine, the process parameters, and then auxiliary systems like drying of the material, part transfer, printing, any additional steps will of course affect quality. And what I should also say is that given the time we have in the webinar today, I've chosen to summarize a bit and try to highlight some examples, but obviously we are available for discussions later on as well, and there's plenty of information to be found from other sources too if you want more detail. But given these 6 things I've listed here, I would say that part design is very important, and keeping it simple is important. One of my colleagues at Thule has this quotation printed out, and I think it's relevant. Good design is as little design as possible, because if you in advance think about how the design of a part will affect other factors, affect the process of manufacturing the part, then you will think twice before you release that design. So I like that quotation as well. And this is what Professor Kadir also highlighted, is collaboration is important. So actually the first thing I will discuss after this slide is how to achieve or key to achieving good quality is collaboration between different parties involved in the process, and of course discipline as well. So I added this because it's a little bit of a softer element to this. It's less related to the technicalities of injection molding process, but it's something that I think has worked really well for us in our organization, and I think is something that I would be happy. I mean, I'm proud to share that this is something we're working with. And I start by saying at the top left there, an ounce of prevention is better than a pound of cure. I like these types of idioms, these sayings, but it's really true that if you stop up, or if you stop early in the process, early in the product development process, and think about the hazards, the risks involved associated to the part, then you can prevent a lot of issues that may come up in the future. So just quickly going through this, you see on the right, I've done a screenshot from this document that we have, but we call this the DFM process, Design for Manufacturing. And we actually have segments of DFM for different types of processes, but we've put more focus lately on adapting this more specifically for injection molding. And what it really is like a checklist of questions. And this can appear tedious and it can appear time consuming, but I feel it's a very good thing because you can always fall back on this and double check that you have thought of all the things that are associated with the injection molding process. What I've said here is also that we've integrated this into our project management system, which means that when we are designing a new product, the project managers must report on the status of this DFM process before they are allowed to go to the next phases in the project. And this process gives us a hands-on, direct discussions with the different stakeholders in the project. That means design engineers, it means the industrial designers, it means the structural analysis team. It also means purchasing and later on in the process or at the appropriate time, also ability to involve our injection molding partners. That's another thing I should say is that Thule does not have, we do not do our own injection molding in-house. We work with our suppliers to do the injection molding process. But if I just quickly show the types of things that pop up in this process is having the ability to ask these questions. Have surface texture requirements been defined? Is the wall thickness even throughout the part? And that these are open-ended questions because it should spark a discussion, because for every part, the requirements will be different. But having this discipline of going through these types of questions and doing this continuously throughout the different phases of a project, I think is key to achieving quality, because you don't want to end up in a situation where you have a finished part design that's released and you're asking the injection molder to fix it with their process parameters, and you are finding out that because the wall thickness is uneven, then there's limited things you can do. You want to identify these types of issues early. So I would recommend to have a look at how you are working with your quality process, or how you're working with your development processes, to see if there's room available for a type of tracking process like this DFM. And if you want more information about how I work on this, then you can always contact me later on as well. But I'll move on now to a little bit more of the technical things and some examples. So best practices for injection molded part design. And this is in summary again, but first thing I tell my colleagues who are designing parts is maintain even wall thickness. As was mentioned already, plastics do not conduct heat well, so thick parts take a longer time to cool, increasing cycle time, increasing cost, but also thick parts give a risk for voids, as Professor Kadir also explained already. But then at the same time, thin parts are difficult to fill, but the takeaway really is avoid variations in wall thickness. Try to maintain even wall thickness throughout the part. Another thing is the gate. It's interesting how simple this is, but at the same time, it seems so complicated and gives rise to so many different questions. It's just to think about, without a gate, you cannot fill the part. You cannot have an injection molded part without a gate. And too often we see that the gate location, the gate type, any kind of discussion about the gate pops up too late in the process to be able to do anything very relevant with this. So, but with an inadequate gate or intake, the part will suffer no matter how well the actual part is designed. Shrinkage, Professor Kadir already discussed some of this, but I would say the main thing is expect shrinkage and warpage. So don't end up in a situation where you are surprised because the part warped. Try to consider the aspects that affect warpage as you are designing the part. And then it's all interconnected, of course, because I point out here, allow for full packing of the part. If you have uneven wall thickness and if you have an inadequate gate, you cannot fully pack the part, and then there's greater risk for warpage. So these things all work in harmony. Going quickly through the last three things here, applying radii to avoid sharp corners in a structure. Obviously, sharp corners, they concentrate stresses and those become failure initiation sites. So adding adequate radii to achieve the mechanical requirements is good practice. Reinforcement ribs, I just add this because it's a very common feature to mechanical or structural parts. And there's a variety of solutions, but as already discussed, there's a big risk for sink marks and poor filling. I have an example of how you could say the rib structure prevented us from getting properly filled part. And then here also, another example I will talk about is related to weld lines. So if you have holes or other features, including if you have multiple gates on a part, then inevitably you will end up with weld lines. So of course, try to avoid this if possible, but then the other thing is work to position the weld line so that it shows up on an area that is not as sensitive. And again, I have some examples to kind of show how this can look like in real life and what kind of steps we've done. So I have three examples today, and the first one is related to the gate. So talking a little bit about the gate, again, it's never, you can never put enough emphasis on this, but without a gate, there will be no part. So you should have an emphasis on the fundamentals, the gate type, the gate location, and the gate size. What I pointed out here actually in smaller text is often this is in conflict with aesthetic requirements, but this is where also you need to collaborate with your colleagues and understand what the requirements on the part are, because if the aesthetic requirements are dictating your position of the gate, then I'd say you may end up in a situation where you have a mediocre or inferior part because you wanted an aesthetically pleasing surface, and then you should take a think about why is that an acceptable scenario for you. And what I'd say is also the type of gate and the location affects just about all aspects of part quality, and this is why it's so important, because it affects your ability to fill the part, the ability to pack the part, material properties if you have a small gate and you apply too much shear to the material in the process. So the gate is very important. And I have an example here where I've anonymized it a little bit, but quite a large part, a half-kilo part made with the glass fiber. Oh, it's a spelling mistake here, but a glass fiber reinforced polyamide 6. So this is an example from a real product. So we had this large part, just over half a kilo, and prominently visible. So we had aesthetic requirements on this part. And the size of it was about 40 centimeters long. Now, we saw quality issues with this part because in certain misuse scenarios, the part would fail, it would fracture. When we took a closer look at the part, we saw that it was underweight. And I'm happy that Professor Kadir emphasized this, because it's quite frustrating when I see parts that are underweight, because this is such a simple thing to measure, to check, is the part actually meeting the expected weight? But because this part was 6%, approximately 6% underweight, we knew something was amiss, and we could observe voids near the failure area. So with support from our material supplier, we did a scan of this part, and I highlighted this area where we actually saw, you may see a little bit of voids here below, but actually there was this large pocket of that was not filled with material near this area where it was connected to an aluminum profile, and this is where the failure would occur. So this was obviously concerning. And I think we have a question later coming on about how you troubleshoot. What is your approach when working with these quality issues? So one thing we looked at is the gate. And at first appearance, the gate looked to be about 5 millimeters in diameter, but actually this was a mistake, because if we look, this is an image taken from the design or from the CAD design of the tooling. You see that the actual gate that was used was a tunnel gate that went onto the ejector pin. So when at a casual glance, what you thought maybe was the gate was the actual ejector pin mark. But of course, this type of gate, a tunnel gate, which was used to avoid a large gate mark on the part, meant that the actual gate was much, much smaller. So limited our ability to fill the part, limited our ability to pack the part, which resulted in these voids and in an underweight and poor quality part. So we were able to fix this by material selection and increasing the gate size as much as we could, so that we got an adequate part. But what I'd say is that in the next generation of this product, we have emphasized the need for a 6 millimeter diameter sprue gate directly onto the part. And in this case, the gate location will be covered by another plastic part that is part of the product. So in this way, we have both achieved good mechanical quality in the part because of the large gate, but we've also found a workaround for the aesthetics, because we're covering up the gate location. And just a quick thing about the lessons learned here is I'll ensure that the gate is adequate to properly fill the part. It's a fundamental thing. And then here again, coming back to this DFM process that I spoke about a bit, is communicate the requirements and concerns early between the different functions, because you don't want to end up in a scenario where perhaps the design engineer is saying, no, we are absolutely not allowed to have a gate on that area, while there are different workarounds available as soon as you start speaking to each other, you can find a new solution. So I have two more examples. They shouldn't take that much time, but here's an example of a part that is for a bicycle carrier, a roof mounted bicycle carrier, and the shape of it is well, you can see it's a wheel holder, so the wheel of the bicycle will rest in this part. And you can see there's a hole, well, a hole in the middle of the part, so the melt fronts will meet at some point and cause a weld line. And weld lines are problematic in two ways, both aesthetically, because you can get poor surface finish, but then where the melt fronts meet, the material properties are weaker in that area. So this is a problem. And in particular, if you're using fiber reinforced materials where the glass fibers are meeting in an less than optimal way. But here you can see just an animation from a mold flows or a mold filling simulation from Moldex actually, but where the weld line was meeting right here in the middle. And this was a problem because because of the geometry of the part meant that we had a weakness there, and in certain cases the part could fail there. So what did we do? We proposed different design alternatives, and the reference here with the red line marking where the weld line ended up approximately. We had a scenario where we modified the wall thickness. So we actually made one side of the part thicker than the other, and just a little bit. It didn't affect the part, let's say, significantly. It didn't add a lot of weight. It didn't affect the warpage of the part that much, but it pushed the weld line to the side. Another scenario that we looked at was adding a rib in the center here so that we would actually get 3 flow lines, one on each side and one through the middle, and then we would get a weld line on either side. Actually, there should be a red line here as well. But so we would push the weld lines away from this sensitive area in the middle. So there's, if this is an example of where we thought of, a thinking exercise about we knew the weld line would appear there and what kind of things could we simulate in a mold filling simulation to decide what would be an appropriate alternative design for the part to avoid this quality problem. And the last example I have here today is from the cover for a roof rack. And this was actually one of the first things I worked on when I joined Thule a few years ago. And I didn't have a very good image, so I took an image of a different roof rack product. But essentially what we're talking about is this cover that goes over the top here. And it should be both, I mean, you see the brand is very visible, and this is on the roof of the car, so it's in your line of sight. It has high requirements of good aesthetic performance, but it should also fit well because it's a cover, and have certain mechanical requirements as well. What we saw in this part was that when we were working with our partner injection molder was that we initially saw burn marks at the end of fill. And it may be difficult to see in this picture, but the aesthetics were poor in this area. So what did we do in the process trials? And this is where I think it's interesting because it joins both the process parameters with the design. So we had the design finished. So what could we do with the parameters? We needed high injection speeds to fill the part, which led to burn marks. So if we dropped the injection speed, moved the switch point over point earlier, and then relied on increasing holding pressure and holding time to fill the part adequately, we got poor surface finish, as you might see with these ripples in the part. And with the higher holding pressure, the ejector marks were visible on the part. So this was not an option either. So we had to find a compromise by increasing the venting, increasing the ability for the air to escape from the cavity, which would allow then higher injection speeds, but with some risk for flash. And this is all a discussion about process parameters, but then I added this little schematic here because this is really what was happening in the part, is that inside the cover, there was certain rib structure, but the ribs were thinner than the general wall thickness of the part, which meant that the reason for this is because, as Professor Kadir mentioned, is that ribs there's a risk associated to have sink marks, which is not acceptable. But because of these thin ribs being so much thinner than the general wall thickness, they were the last to fill. And as the schematic shows, even though this rib is early in the process, it's the last to fill because the material will preferentially flow in the thicker areas. So if I tie it back to the parameters, we had to get very high injection speeds to fill the part because of these thinner areas. We had to have the material to be the opposite of viscous, let's say easy flowing enough to fill those thin areas, so that we could fill these thin ribs and fill the end. But this, of course, had a knock-on effect with the burn marks. So it's not a straight, I don't have a straight solution or an easy solution for this, but these types of here it was the time of the part affected had knock-on effects of what our injection molder was able to do with their process. And in the end, we found a compromise that was acceptable, and I think that just highlights the importance again of collaborating with your partners to achieve good quality. So with these 3 examples, I'll finish up by saying, and these again are quite like softer principles because you can find a lot of technical data, and there's a lot of technical documentation available from material suppliers and online, or you can, and of course we can talk if you have any more specific questions later on. But what I would emphasize is striving for simplicity. A simpler design makes it easier to maintain a good and a straightforward process. Use some kind of design for manufacturing process. Design the part with the process in mind. And if you are not experienced with the injection molding process, then make use of the wealth of experience and knowledge that exists within other, within companies that work with injection molding, or universities like Jönköping University. Use risk assessments and checklists. This is connected to design for manufacturing. And then again, collaborate early and often, because you should not feel achieving quality is not a one person job. It's something that you do together as a team. And with that, thank you for your time. And I think this is a part where you may have questions as well.
Thank you, Tor, and also Irfan for the presentations. Is there any question to?
No questions so far.
All right. As Tor was also mentioning, there's possibility to raise your questions either now throughout the webinar or even after the webinar. You can contact us and raise your questions. So welcome to do so. Again, I thank both Irfan and Tor for very, very interesting presentations. It was to me, very nice combination of theory and some case studies, what is going on in real cases in industry. Now we are moving to the second part of the webinar. As Stefan was mentioning, we are trying to make these webinars a little bit more interactive. So we would like to have your contribution as discussion to this topic as well. But I understand some of you might have other duties, and if you have to leave, we would like to thank for your time. We hope to see you again in our future webinars. Every 2 weeks, within the course of 2 years, we have different webinars related to metal and polymer. You're welcome to join any of the webinars. But we would love to have all of you still in the webinar. We would like to have the discussion regarding some specific questions related to the topic of the webinar. So more than welcome to stay for half an hour more. I will divide you into three, or I will propose 3 different rooms that you can join yourself. As you see somehow on the screen, and I think Stefan is also sending you the questions in the chat. You can see them. There are 3 different questions that each question will have a separate room that you're welcome to join. And while you're discussing, we would like you to summarize the notes while you're discussing with others. And after we come back to the main room, we will try to wrap up for each of the questions. So please read the questions in the chat, and soon I will invite you. I will create the rooms. You see the options on your screen, and you can join any of the question rooms that you would like and discuss.